investigating quantum computation, but the goal today is to achieve this with a purely classical server, so no quantum capability at all required of Alice. So there's a couple ways by now that are known how to do this. One is the work of Mahadev from a couple years ago, which achieves it under computational assumptions, so assuming the post-quantum hardness of the learning averages problem. And I'm not going to talk about that. The other way, the first time was achieved, this was by Reichardt, Unger, and Vazirani from 2012. This is 18 or something. And this is information theoretic, so there's no hardness assumption, but it requires the use of two quantum servers that share entanglement. And so I'm going to set this up. The reason I chose to present this, there's a couple reasons. One is I think that it's more accessible than that work. That's a little bit harder to digest. And the other is that we'll see in the course of the proof that it demonstrates something that I think is very interesting and very powerful about entanglement, which is the kind of constraints that you can put on quantum systems through only correlations, classical correlations that these systems generate using entanglement. So I'm not going to present their protocol because it's also kind of complicated. I'm going to present a much simpler protocol that's due to Grillo from last year. So that's the plan for today. And we're going to achieve this in a number of steps. So the starting point that I'll take is going to be a very different starting point from the first two lectures. So in the first two lectures, we were working in the circuit model. So Alice had a circuit, an input, and she wanted the server to perform the quantum computation that's described by that server on the input that she cares about. We're going to solve the same problem, but we're going to do it in the what I could call the Hamiltonian or the local Hamiltonian model of computation. That's a starting point that's inspired by the techniques or the results that Sandy described in her talks. So let me start with that, describing the setup. So it's something that's been called post-hoc verification. I mean, this is not a very standard term. You'll see what it means once I describe it. So my starting point is something that I'm going to assume that there exists the following kind of transformation. So the transformation takes as input C, which is a circuit. So it's an n-qubit quantum circuit. It has T gates. And then there's an input X. I'll take it to be a classical input. So X in 0, 1 to the N, which is an input to the circuit. And the transformation is essentially this circuit to Hamiltonian transformation that Sandy described. So it takes as input this. It's an efficient classical transformation that produces a local Hamiltonian. In fact, you'll see why I'm going to construct two local Hamiltonians. One of them is going to serve as a witness for the claim that the circuit returns 0 on output input X, and the other, the claim that the circuit returns 1. So you'll see why there's two Hamiltonians. Let me just write here. So H0 and H1, two local Hamiltonians. On a slightly larger number of qubits. So, sorry, my notation, I want this to be M. The reason is I want to reserve n for the number of qubits on which the local Hamiltonian acts. So this n is going to be a little bit bigger than m and t, but not too much bigger on n qubits. Such that. And I'm going to require three properties of this transformation. Well, one is that it's efficiently computable in classical polynomial time. I'm not going to write this. The properties are going to be, one is, what is the form of this Hamiltonian? I'm going to assume, just for simplicity, for the sake of the lecture, a very simple form of the Hamiltonian. So such that HB, for each B in 0, 1, has the following form. So I can write it as 1 over 2n, sum for I equals 1, I want this to be normalized, so 2, n choose 2. So sum for ij going from 1 to n of some coefficients alpha ij xi tensor xj plus beta ij zi tensor zj, such that these coefficients alpha ij, beta ij are plus minus 1. Here I'm making a simplification in general. Well, let me write the three properties and then I'll say exactly where I'm slightly oversimplifying. Just notation-wise, so this is n qubit local Hamiltonian. So if n qubits, there's n choose 2 pairs of qubits. And on each pair of qubits, my Hamiltonian is acting as xi tensor xj and zi tensor zj with some plus minus 1 coefficients. Okay? The plus minus 1 is for simplification. Things that these are real numbers and they're kind of polynomially bounded. Second property that I want is that if this circuit C on input X returns bit B with probability at least 2/3, so B could be 0 or 1, that's a measurement of the output qubit of the circuit, then there's a witness for that in the form that there exists a state, I'll call it gamma B. This state is efficiently preparable using a quantum computer, preparable, such that it's a smallest eigenvalue eigenstate for the Hamiltonian, so gamma B, HB, gamma B, and here I'm going to write -1. You can see that because of my normalization, this Hamiltonian has norm between -1 and 1, so the smallest eigenvalue is definitely at least -1, and here I'm claiming that the smallest eigenvalue is achieved. And then the last property is that in the opposite case, so if B is not what I called in the other lectures the correct outcome of the circuit, so if this is less than 1/3, then the smallest eigenvalue of the associated Hamiltonian HB is at least a bit bigger than -1. So -1, and just for simplicity, I'm going to write -1 plus 1 over n cube here.
Can you repeat the second condition?
Yeah. So the second condition is that if this circuit returns a certain bit with probability at least 2/3 when I run it on the input X, so B is 0 or 1, like it depends on the circuit, I'm going to assume that there is such a bit, then the Hamiltonian has smallest eigenvalue exactly -1. That's the first part of the claim. The other part of the claim is that an eigenvector with smallest eigenvalue -1 can be computed in quantum polynomial time starting from the data. So starting from a description of the circuit and the input to the circuit. So Sandy presented such a reduction in a slightly different setting. So she presented it for QMA complete problems. So there the input was a circuit and this Hamiltonian was a witness for the fact that the circuit has an accepting quantum state. Here, my circuit doesn't take any witnesses as input. So it's this is a BQP complete problem, but BQP is in QMA, so I can think of this as a problem in QMA. So I can apply the reductions that she described. Where I'm slightly oversimplifying is that I'm simplifying the form of the Hamiltonian. So in general, this local Hamiltonian might look a little bit more complicated than that. In fact, we can make it look like this, but with polynomial size weights, not necessarily plus minus 1. They could vary a little bit more. And I'm also slightly simplifying here in that in the case where the circuit returns this bit B, then the associated Hamiltonian HB, I'm assuming that it's what's called frustration free, so it has a smallest eigenvalue exactly -1. In general, it wouldn't be exactly -1, it'd be a little bit above -1, and this would be a little bit more above -1 than this one. But that's just for the sake of the presentation.
Maybe it's worth reminding what are X and Z, especially in the context of the Hamiltonian.
Okay, sure. So they're just, X is just this matrix, it's observable, and Z is this matrix. Oops. So they're observables.
Hereby is B enough product, assuming that it's like acting identity on the other.
Yeah. So I used that notation in the previous lectures, and I just mean that if you run the circuit, quantum circuit C on the classical input X, then you get the outcome bit B with probability at least 2/3.
And
Yeah.
how is little x related to gamma?
Gamma depends on X. So X and C, they're really the inputs of my problem. This is the problem that Alice wants to solve. She wants to determine when you run the quantum circuit C on the input X, is the output qubit more likely to be 0 or 1? Promised that there's a clear distinction between the two. One is 2/3, the other at least 2/3, at least 1/3. This reduction, so the two Hamiltonians, H0 and H1, they depend on both C and X. And gamma is defined as the ground state of the Hamiltonian. The Hamiltonian depends on C and X, so gamma in general depends on C and X.
There is H0 and H1.
Both of them depend on C and X.
And gamma is an eigenstate of which of the two?
HB. So there's two gammas. There's gamma 0 and gamma 1. And
Gamma has an index B.
gamma 0 is yeah. Yeah, is that okay?
So is number 3 expressed as a for all gammas, or it's that?
Yeah, I mean, it says that the smallest eigenvalue of HB. So yeah. So every gamma has smallest eigenvalue. Let me maybe use this in order to design a simple delegation protocol that we'll build on, and maybe it makes it a little bit clearer. And if it's still not clear once I describe the protocol, then I'll go over it again. I think I'm not going to need this, so let me describe the protocol here. So this Hamiltonian is nothing mysterious. It's really just the circuit to Hamiltonian, the Hamiltonian that's obtained from the circuit, Kitaev's circuit to Hamiltonian construction applied on the circuit C. The input X doesn't really matter. You can consider it to be part of the circuit C, where the first step of the circuit is starting from zeros, create X, and then run the circuit. And that would be a fixed circuit that is run on 0. And if this circuit returns 0 with probability 2/3, meaning it accepts, then the Hamiltonian should have a small eigenvalue, and if not, it should have a large eigenvalue. Okay. It's just that in context of decision problems, in the context of Sandy's talks, we're just interested in knowing if this circuit returns 0 with probability bigger than 2/3. That's it. And so we just create one Hamiltonian that's supposed to, that is associated with that decision problem, the set of all C and X, such that C on X returns 0 with probability 2/3. Okay. Here I'm just saying I'm considering two decision problems. The set of all C and X such that 0 is returned with probability at least 2/3, and the set of all C and X such that 1 is returned with probability at least 2/3. Okay. Okay, so here's a delegation protocol, a simple one. So there's Alice and their server. Alice has as input a circuit, C, and an X on which she wants to evaluate the circuit. So this is exactly like last time. The first step is that she's going to compute using this reduction over there, H0 and H1. And she's going to send all that information to the server. So the circuit, the input to the circuit, that's what she cares about. And then the Hamiltonian, the server could have computed itself, but let's just send it over. In particular, Alice here is giving like all the information about her computation to the server. So these protocols are not going to be blind at all. That's just a limitation of that kind of protocol. And I'm interested in verifiability, not blindness. Okay, so Alice just tells everything to the server. The server is not going to be trusted. Here's what they're supposed to do. The first step is that they're going to determine what I call the correct B by running. So they run the circuit maybe multiple times, C on using their quantum computer, and using that they determine if this circuit returns 0 or 1 more often than not. So for this correct B, we're in situation 2. So this is the B that's returned by C on X with higher probability than average. Then they can prepare the state gamma B. So they would prepare gamma B, and they would send this back to Alice. So they'd send back to Alice first, what is the answer? So this is just saying, well, I ran your circuit and I saw that the answer is 0. Let me tell you. So it would be fine if the server is honest, but in general the server can be dishonest, and so we want them to give us a proof that the outcome is indeed 0. And this proof is this gamma B. So she's going to also send gamma B, but let's think that she sends it 1 qubit at a time. Okay, so it's 1 qubit at a time. This is just a way to think about it, that the server sends it 1 qubit at a time. Okay. Now here's what Alice is going to do. She's going to look at B and she's going to think, well, okay, that's probably the outcome of the computation, but let's check. How do we check? Well, I want to make sure that this gamma B is an eigenstate of eigenvalue -1 of the Hamiltonian, and so she's going to implement the verification, the quantum verification procedure that Sandy described in her talk in order to check that a candidate state is a ground state of the Hamiltonian. Here, because the Hamiltonian has a very simple form, she can do it pretty simply. What she's going to do is first she's going to select just a pair of qubits that she wants to check, so that's associated with a local term. So she'll check, sample ij uniformly at random from 1 and n. That's the possible locations. And she has to check either the x or the z term. So she's going to select a basis uniformly at random in x and z. And then she's going to measure qubit I in the basis W, and she'll get an outcome OI. these are observable, so I'm going to write the outcomes as plus minus 1. Then she's going to measure qubit j in the same basis. She's going to get an outcome oj in plus minus 1. And then she's going to accept if and only if the product of these outcomes has the correct sign. So is equal to alpha ij in case I was looking at the x basis, and beta ij in case I was looking at the z basis. That's really the same verification procedure as Sandy described. I think maybe in her talk these were projections. Were they projections in your case, or did you do observables for the local Hamiltonian?
They were just general Hamiltonian cells.
Okay, so they're just observables like this, and you'd measure in the eigenbasis of these observables, you look at the outcome, and then you have a coefficient there, so you might want to flip the outcome if this coefficient is minus 1, but then that's it.
Alpha and beta depend on B.
Alpha and beta depend on, yes, so they depend, they're the coefficients of the Hamiltonian HB. So, yeah.
There is B on the left-hand side, but there is no B index on the right-hand side. In this definition of HB.
Oh, yeah, sure. That's because I was trying to keep the notation a little light, but yes, thank you. I could write it like this. So, and this is alpha B and beta B. Right, otherwise Alice's verification procedure wouldn't depend at all on B, and so that wouldn't make sense. Yeah. And so the claim here is that if this B that's returned by the server is the correct outcome, and the server is honest, so they prepare the correct ground state, so then Alice accepts with probability 1. So that's the first part of the claim. And the second part is that if B is not the correct outcome, then whatever the server does, the probability that Alice accepts is at most 1 minus 1 over, and then it's going to be something like, there's this gap n cube over there, and then there's also the fact that she checks only a random term, so it's going to, well, no, that's already incorporated, so something like this. Okay. This is because in the honest case, then this gamma there, the fact that it's equals minus 1, oh, so this would be minus alpha ij, sorry. Minus,
And what's written after that? Something?
yeah, sorry. So that's in case the measurement basis that she chose is the x basis. So she's just choosing, there's many terms that she could check. She's just choosing one of these terms at random. She's making the measurement, and then she wants to check that this is supposed to be an eigenvalue minus 1 eigenstate. So the outcome of the measurement times alpha should be equals to minus 1. So which means that the outcome should be minus alpha or minus beta if she chose to measure in Z. And so the claim is that if B was the correct outcome and this gamma satisfies the point 2 here of my reduction, then Alice is systematically going to see outcomes that she accepts. Whereas if B is the wrong outcome, then we're in case 3, and then whatever state that the server sends to her, this state cannot have energy minus 1, so it must violate at least one of the terms with some probability. On average, it violates a random term with probability 1 over n cubed, and so the probability that she accepts is at most 1 minus 1 over n cubed. Yeah?
For number 2, I don't see how you're getting exactly minus 1.
Yeah.
There's still probability of error.
Yeah, so I mentioned that. So this is an oversimplification. So I'm making two oversimplifications here. One is that the coefficients, I'm assuming, are exactly plus minus 1 instead of just like real numbers in some bounded range. And the other simplification is that in case 2, the smallest, this Hamiltonian is what's called frustration-free. And in general, this doesn't hold as is, but it's to simplify the presentation. Everything I say can be extended to the actual claim.
But this doesn't look frustration-free.
It is, because the norm of this Hamiltonian...
The pair commute. Yes, sorry, it's okay.
Okay. Okay.
Solved it myself.
Yeah?
It looks like Alice still accepts with pretty high
Right. So this is not a very safe protocol. You'd want to repeat it. So you can amplify this. I'm not going to do the details of this, but you can amplify in two different ways. You can either do sequential repetition. So just repeat it many times. So simply ask her for many gammas and just measure them. And you can show that this, even though the server could cheat and give you gammas that are entangled or things like this, you can show that this amplifies the... And you can even do it in parallel. This is slightly more non-trivial. It's not like a black box amplification, but you can also amplify the success probably in parallel. Well, what I described actually is the same, in fact, because, yeah, anyways. So you can amplify just by asking for more copies of the witness. So still, it kind of fits the kind of delegation protocols we considered in the previous couple of days, because Alice here doesn't need a big computer. In fact, she needs a 1-qubit quantum computer. This is why I wrote receive the qubits one at a time. She can receive the qubit, she can decide who she's going to measure ahead of time, and then she gets the qubits, and if it's not a qubit she wants to measure, she throws it away. When she gets one of the 2 qubits she wants to measure, she immediately measures it and stores the outcome, and then the other qubit measures, etc. So she just needs 1 qubit, and only the ability to perform these kinds of measurements on her qubit. Right? So it's pretty simple from the point of view of Alice's quantum capabilities, but I want to do better. I want to make Alice entirely classical. So that's just our starting point, and then I'm going to modify it in a sequence of steps. Yeah? Can you speak a bit louder? That claim here? Yeah, so that claim is saying that suppose that I execute this protocol, okay? And the claim has 2 parts. The first part is that suppose that the server, having seen my circuit, my computation, gives me the correct value B, and also they give me the correct ground state of the Hamiltonian. Then Alice, in this procedure here, is always going to obtain outcomes that satisfy her check. So she'll always say, yes, I accept the server's claim that the circuit returns B. That's the first part. Huh?
Why is this check correct?
It follows from this part here. So that part says that gamma B is a eigenvalue -1 eigenstate of the Hamiltonian. This Hamiltonian is a sum of terms, and you can check that the only way for gamma to be an eigenvalue -1 eigenstate of H, it has to be an eigenvalue -1 eigenstate of each of the terms. That's because the norm of H is less than 1, so it's extremal in that sense. So it has to be an eigenvalue -1 eigenstate of this and that, which means that if I measure gamma in that basis, I am going to obtain an outcome that is whose product with alpha is -1, or whose product with beta is -1, and so it checks. So it follows from that. And the part 2 follows from part 3 here for the same reasons. Yeah?
It seems a bit wasteful in the sense that you're not using most of the bits. Couldn't you think of a case where instead of picking 2 bits, you just, for each one of the qubits, you select either X or Z at random, and
Yeah.
measure all of them, and then does it give you anything?
I mean, it doesn't matter. It doesn't matter because these things are very loose. So, I have this n cubed there, and so maybe you're going to shave. Maybe you'd end up having n squared instead of n cubed here. You'll save a little bit. So, fine. I don't care.
You cannot get to a constant in this way.
No. No, that would require some kind of PCP. That would imply some kind of PCP. Okay. Other questions on this? Okay, so I want to do a couple steps on the protocol, so I'm just going to keep this protocol here and change it in a couple ways, and the second way is going to be the most significant. Maybe we keep this here. So let me actually do it in one step because it'll be, I think it's clear in this way. So the idea, you have to think that the idea is that now Alice is still doing a quantum computation, but I have simplified the problem. This quantum computation that she's doing is much simpler than running the original circuit. She's just getting all these qubits from the server, and she's just making very simple measurements on them. I'm going to use a second server, and I'm going to delegate that quantum computation to the second server. Because it's a very simple quantum computation, I'm going to manage to delegate it to the extra server in a completely classical way. So the original computation was quantum, I delegated it in a partially quantum way, and now this partially quantum way I'm delegating classically to a second server. Here's how we're going to do it. So in fact, sorry, let me use this board. So here are the 2 servers, server 1 and server 2. and here is Alice. I'm just going to describe what these servers are supposed to do. So they're supposed to share EPR pairs. So this is a quantum state between them, and this quantum state is made of n EPR pairs. The first thing that Alice will do will be the same as here. So she's going to send her circuit C, her input X, and a description of these Hamiltonians to server number 2. So server number 2 is this server here. I guess I could call it 1, but never mind. So this server number 2 is going to compute the correct B. And they're going to prepare here. So I'm drawing it as if it was just 1 qubit, but think of this as being n qubits. They're preparing this state gamma B here. Okay? And then they're going to teleport it to the first server. That's what they're supposed to do. So they'll make a teleportation measurement here. So this teleportation measurement is a measurement of the n qubits in the Bell basis. So it's going to return outcomes A, B that are n-bit strings. And the server is going to report its teleportation outcome measurements to Alice, A, B. Oh, well, let's call them A and C because this B was... and it's also going to send the correct outcome B to Alice. Okay? So the server did the same thing as over there. Instead, the only difference is that instead of shipping the state directly to Alice, Alice can't receive qubits. So it's teleporting the state to server number 1. By properties of teleportation, once server 2 has done that, the state of these n qubits is almost gamma B, except that it's one-time padded depending as a function of the outcomes of the measurement. So there's a X, A, Z, C that's been applied to that state there. Okay. And now Alice is just going to ask server number 1 to make the measurements that she would have made. So she's going to select, as she did over there, I and J uniformly at random qubits, and she's going to select a random basis, X and Z, and she's going to tell all that to server 1. So she's going to send I, J, and W. Server 1 is going to measure the qubits ij in basis W, and it's going to get outcomes OI and OJ. Send them back to Alice. And Alice is going to do the same check as over there, except she's going to correct for the one-time pad keys. So she's going to check that OI times OJ is equal to minus alpha ij, as before, in case W equals X, corrected with the keys. And so in the X basis, you have to correct for the Z keys. So I have to multiply by minus 1 to the Ci plus Cj. You can trust me, hopefully, on the check here. This is just, it's not the exact same verification as here. I'm just correcting by the one-time pad keys to account that server 1 made the correct measurement, but not on the state gamma. On the state gamma, that's one-time padded. And so you have to see how that measurement commutes or not with these Pauli operators, and there's just a small sign change here, depending what these keys are. Okay, so the claim that I want to make about this is that...
Do the server 1 and server 2 trust each other?
Yes. So maybe let me finish the sentence that I was going to make. So the claim that I want to make is that in this protocol, the claim that was on the board before in terms of it being a correct delegation protocol, there's two claims. First of all, is if the servers do everything that's written on the board, then and if B is the correct outcome, then Alice is going to accept with probability 1, just as before. And now the other claim is that if server 1 does the correct thing, whatever server 2 does, the protocol is going to be secure, meaning that they can't claim the wrong B. The reason is that as long as you assume that server 1 does the honest thing, you can really map this protocol directly onto this one. If server 1 is honest, then I can sort of bundle Alice and server 1 together. And then the only difference between the two protocols is really that instead of sending the state 1 qubit at a time, I teleported it. that doesn't make any difference from the point of view of Alice's side. In particular, it doesn't even matter that they actually share APR pairs. The point is that this server 1 is measuring some kind of quantum state here. And in the case of a no instance, in case of a claim for a wrong outcome, there just does not exist a quantum state that would give me outcomes that are accepted. That's by my item 3 over there. Okay. So maybe I can write this a little bit loosely. The claim is that if server 1 is honest, then the protocol is secure. Correct. Yeah? Yeah?
Check alpha ij for the x.
Right. I didn't write everything. I'm sorry. So that's the case where w equals x. And the case where w equals z, it would be beta ij minus, and then you'd correct using the a bits. Yeah. Okay. So I'd like to even claim that this protocol is secure, whatever the server 1 does. And then this would be, that's it, we'd be done. It'd be Alice is completely classical. There's these two servers. The reason would be that why this would not be secure is that this server is told what measurement I'm making. And so in principle, they could change the state that they're measuring as a function of the measurement that I'm making. And so in this case, they could lie about the protocol. What's important is that the ground state or the state that I'm measuring should not depend on the measurement that I'm making. It should only depend on the total Hamiltonian. So they could do that. But then, they report outcomes to me, OI and OJ, and these outcomes I'm correcting using these one-time pad keys that come from server 2. So server 1 doesn't know what the one-time pad keys are. And so it seems like it's pretty hard for them to lie to Alice in the protocol because they don't know what Alice's verification is going to be in the end. So it could be that this protocol is secure, but it's not known. So instead, what I'm going to do in the maybe 20 minutes left is Vika gives me.
The S2 can just send A and C equals 0, for example. And I mean, if the servers are sort of colluding and.
Oh yeah, that's true. You're right. Yeah, that's true. You're right. Okay, thanks. So fine. So it's not secure. Yeah. Thanks, Vika. Yeah. Why did I think?
Can you repeat why it's not secure? Because what?
So because the servers. So as someone was asking over there, the servers are allowed to collude in the sense that they really might want to collaborate to convince Alice to accept the wrong B as outcome for their circuit. One thing that I'm definitely excluding is that these servers communicate with each other.
Agree ahead of time.
But they can still agree ahead of time on the strategy. And the strategy could be that this server here always reports 0, let's say 0, 0, 0, everything 0. They just ignore the input, they just say 0. And this guy can always satisfy the check that I'm making because they know what check I'm going to do. These are 0, so these don't matter. They know what the Hamiltonian is, so they know what alpha and beta are. And they know what I and j I care about because I told them. So they don't need to measure any quantum state or anything. They just need to return to me two values that have the correct parity. The problem is really that they knew what measurement I was making and they could change what they're doing as a function of the measurement that I wanted them to make, and they don't even need to make a measurement, and so they're just lying. So the goal of the second part of the talk is to introduce techniques that are going to allow Alice to verify that this server is doing the exact correct thing. So that when I tell them, please measure qubit I in basis W and qubit J in basis W, this is what they do. They actually have a fixed n-qubit state that doesn't depend on these, and such that when I tell them to measure, they measure. Which is something a little bit surprising because I'm only giving classical instructions to this server. So what do I know that they do in their quantum lab? So I'm going to explain how we can do that. But it's on the side now, so I'm going to write on the board like a much weaker claim than what's needed here, but then I'll focus on the weaker claim because we don't have time to do everything. So I'll write my weaker goal. So the goal is the following. The goal is to design a protocol, like a protocol of that form. So I'm writing this a bit informally, that allows Alice. So this has nothing to do with computation, no? So Alice to verify that two things. One is that these two servers, S1 and S2, they share an EPR pair, so they have a quantum state that's equivalent to an EPR pair. And two, when S1 is asked to measure his qubit, so there's just one EPR pair now, his qubit in basis X or Z, it does so. Okay? So that's really a sub-goal that for the remainder of the lecture I want you to accept as my sub-goal. I'm going to make the connection in just 1 minute and then we'll focus on that. So just to clarify the sub-goal, I want a small protocol like this where Alice is some classical machine, classical computer, and it can exchange information with two servers that are quantum servers. These quantum servers are not allowed to communicate. They might share an entangled state between themselves or they might not. And my goal is to check using only classical exchange of information with them that first of all they do share an EPR pair, maybe other stuff, but at least an EPR pair, so they must have entanglement. And second is when I tell this server to measure the qubit in the basis X or Z, then this is what it does, and it returns to me the outcome. So the claim that I'm not explaining at all is that if I have such a thing, it's a good starting point to fix my protocol here. I'd do this, I'd mix this kind of test with the test that's there in order to make sure that the server 1 is honest. And so we can use my claim about this protocol being secure when server 1 is honest. Of course, it's much more complicated because here there's just one EPR pair, here there's n of them, I'm asking to measure 2 out of the n, etc. So there's a lot of work that needs to be done, but I want to talk about this as a starting point. Is this okay? Yeah?
The fact that if you can verify that he measured, it doesn't mean that he will tell you the right measurement.
Is asked to measure qubit. It does so and reports the outcome. So yeah. I'm going to make this goal into something more precise, so you'll see exactly what I mean by this. Because, but yeah. Other questions on where we're at now? Yeah.
Why do you require one?
Why what? Sorry.
Why do you need to verify one? Like they have an API pair. If they have less power, then it wouldn't bother you.
The part that I really care about is more the item 2, because this is what I need to analyze my protocol here. To make sure that this is secure, I need to make sure that S1 does the correct thing. I need to make sure that when I tell them measure I, J in basis W, they do it. Because in my sort of basic protocol, this is what Alice would have done. She would have just measured qubits I and J, and if she did this was secure. So I want the server to do that. And so it doesn't need to be an EPR pair for this particular application. But what's important is that really they measure in the basis that I tell them to measure. If they measure in a different basis, they're kind of implementing a different Hamiltonian, and then, I don't care about that different Hamiltonian. I really care about my Hamiltonian H0 or H1. Is that okay? Or? The EPR pair is going to be used to verify that they make the right measurements. It's kind of a, yeah. If I could, if I could do this, but I would have only one server, no EPR pair, and just say, well, I can check that this server makes measurements X and Z, then that would be better. But I don't know how to do it if it doesn't involve an EPR pair. Yeah?
Can you explain again what happens with the one-time pair? Where did that come from?
These here, or? Well, it's because, so if you remember the first protocol that I drew, there the server was just giving you the quantum state, the ground state, and then you just measure it in the right basis, and then that's it, right? Now, the way I set it up is that this server is supposed to teleport the ground state to that server. Teleportation doesn't work exactly. If you teleport a state gamma b here, you don't get gamma B. You get gamma B and then you have these corrections. In teleportation, the server would send the correction bits, and this server would be able to undo the thing and then perform the right measurements. I don't want this because I don't want these two guys to communicate with each other. That would break my security. So then it has to perform the measurement. There's no choice. It has to perform the measurement on the one-time padded state. But then the outcome that it gets are going to be a little bit changed depending on the one-time pad. And so Alice accounts for that. She knows the one-time pad. She accounts for that. Is this okay?
Yeah.
Okay. Okay. So we're going to achieve this. And even though you're right that I don't need an EPR pair, this is how I'm going to get there. And so the starting point is going to be something that I might only have showed up in Orr's lecture on the first day, which is the CHSH inequality or the CHSH game. And this is going to be my starting point. So I'm going to remind you what this is. So this is a little bit of an aside now, but we're eventually going to achieve this. So here's one thing that showed up in Orr's lecture, and I think only in Orr's lecture. I don't know. So yeah, only in Orr's lecture. Okay, so let me give you everything then. So this is a little bit of a protocol like this, but take it as a self-contained thing. So imagine that we have two servers. Okay, and they share entanglement, they don't share entanglement, it doesn't matter. And there's Alice, and here's what Alice does. She selects a pair of, I call them questions, but these are just uniformly random bits, 0 and 1. And she sends X to server 1 and Y to server 2. These servers perform some kind of computation, they do what they want in general, and this one returns to me a bit A, that's a plus minus 1 value, and this one returns a value B, that's plus minus 1. Okay? Maybe it's the outcome of a measurement on the quantum state, or maybe it's just something they cooked up. And Alice is going to check that the product of A and B, so the product of these plus minus 1 values, is equal to minus 1 raised to the X and Y. So there's not so many cases, so you can check what this means, right? What this means is that if X and Y are, maybe I can write it here, X, Y, if they're 0, 0, 0, 1, 1, 0, 1, 1, then the product of A and B should be 1, 1, 1, and minus 1. Okay? So what these guys are trying to do is that if they're given any of these inputs, they have to give outputs whose product is plus 1, and in this last case, the product should be minus 1, so they should be different. And so why this is interesting is because you can show the following two things about it. The first thing is that if S1 and S2 do not share any entanglement, and also they do not communicate, right? That's always the background assumption. Then the probability that they win in this game is at most 3/4. So what's the game? Again, Alice chooses, so the probability is over this choice of questions, right? So there's 4 possibilities, they're chosen uniformly at random. Also over any kind of probabilistic or quantum computation that these servers could make. My claim is that on average, if I repeat this many times and the servers do not use any entanglement, the maximum probability with which they can satisfy Alice's check is at most 3 out of 4 times. And you can prove this by yourselves just by enumerating all possibilities. The reason this is difficult is that, say you're Alice, server 1. And server 1, let's say, gets a 1, okay? Well then, depending on server 2's question, you have to reply the same thing as them or a different thing. But you don't know what their question is. And so you don't really know if you're trying to reply the same thing as them or the opposite. And that makes it kind of hard to coordinate. Okay, if I only wrote this, it wouldn't be that interesting. But the interesting thing is that if S1 and S2 share one EPR pair, then they can achieve a winning probability that's bigger. So that's half plus 1 over 2 root 2. So it's 0.85. Okay. So this is kind of well, this as it is, it's due to CHSH, their authors. So this is a very old result in quantum information from the 60s. And it's kind of one of the foundational results in the theory of entanglement. This is what we say when we say that entanglement allows to generate non-local correlations. It's exactly in the sense that there are some simple checks like this that Alice could make, such that if you don't have any entanglement, the maximum correlation that you can get, I mean, we think of this as a correlation, is some number, like 3/4. But in the quantum case, using entanglement, you can get a bigger number. And so this, even in the context of the discussion about supremacy or things like this, this is a claim of quantum supremacy, right? It's a claim that there's a certain task. It's not a computational task. It's just a statistical task that can be achieved better using entanglement than not using any entanglement. And that kind of supremacy has been verified. So people do experiments, so you can do this and you can check and you get 0.85. So this works. So any questions on this? For those of you who might not have seen this, I mean, I think a lot of people maybe have seen this before, but if you have not, yeah?
What about creating entanglement as a binary thing?
Can you speak a little louder?
Yeah. In this game, at least, you're creating entanglement as a binary thing. You either have entanglement or not, and if you don't, then you lose. It has to win with this threshold. Can there be a situation where they share it?
Yeah. Yeah. So the question is, are there intermediate situations? The answer is yes. So it's definitely possible to share something that's a bit weaker than an EPR pair. So it's not maximally entangled, it's a bit more weakly entangled. And then you'd succeed with probability maybe 0.8 or something like that. So that's possible. What's very interesting about this game that I'm going to put on the board that's relevant for us, and that's a little bit less well known than this. I mean, this is very well known. I'm going to now write an old theorem of Werner and Summers' theorem from the 80s, I think, but it's less well known. And the point is that, sort of a slight contrapositive to what you're saying, which is that there's essentially a unique way to achieve this 85% probability. So if you achieve 85% or 84% or something, the only way to do it is really to be sharing an EPR pair, and on top of that, to making measurements on that EPR pair that are the measurements that let you achieve this, that happen to be measurements in the standard and Hadamard basis, depending on what the question X is. So this is one way to achieve 0.85, but it's the unique way. And so that's going to be useful for us. And so let me write it on the board. Yeah?
But in this game now they check that they have some EPR pairs, but they may not use any EPR pairs to teleport state gamma.
Let me write this.
Check it on the wrong things.
Let me write a slightly technical statement and then argue about it and then answer your question, and we might actually arrive at the end of the lecture already. So let me write a lemma. So this is this theorem by Werner and Summers. So the lemma says the following. It's not going to answer your question directly, but I'll get back to it afterwards. So the lemma says the following. It says, suppose that, server 1 uses observables A0, A1 on CD. Server 2 uses B0, B1 on CD, and they share a state psi in CD tensor CD. So the first claim is that, whatever they do, even if it doesn't involve any entanglement, even if it doesn't involve any quantum, I can model it using this kind of information. Okay. See here, I'm not assuming that the state is entangled. It's just like whatever state of their systems is at the start of the game. And then in that protocol, server 1 gets an X. This X is 0 or 1. They return a value A that's plus minus 1. Whatever they do, it could be a classical computation, it could be a quantum computation, it doesn't matter. I can capture that in an observable. This observable is just captures everything, the whole computation that they do, and it specifies, it represents what their outcome is. So I can always do this. But then let me assume that suppose uses observable such that they win with probability at least, well, let's say that they win with the optimal probability, and then I could weaken it a little bit, but Okay, so let's suppose that these observables and this state this. Okay, so then I claim the following. I claim that there exists a unitary U that implements an isomorphism between their space and the space of a qubit tensored with some remaining space, such that this unitary, two unitaries, U1 and U2, such that if I apply these two unitaries on the state psi that they share, then out pops up a EPR pair tensored with some remaining things. So this is EPR. And also, if I apply the unitary after Alice's observer 1 is observable A0 on the state psi, then I would get the same effect as applying an X on the EPR pair. And I have something similar for A1, but A1 is going to give me a Z here. So, okay, so what is this statement saying? Let's go over it again. The first part is just modeling what the servers could do in the CHSH game. And in general, whatever they do, I can model as sharing a quantum state. Could be an entangled state, could be a non-entangled state, doesn't matter. And making measurements on that state. These measurements capture any kind of computation you could make. But suppose that whatever they do, I do observe that they succeed with probability like the optimum probability, or let's say close to the optimum probability. Then I can make like a structural claim about properties of how they manage to achieve this. And here's what I can say. I can say that the state that they're sharing doesn't need to be directly an EPR pair, but up to local rotations. So this is a rotation on server 1 system, a rotation on server 2 system. It looks like an EPR pair, and maybe some other things, but there is an EPR pair. Local rotations cannot change the entanglement, so in particular this state psi has some amount of entanglement because I can create an EPR pair out of it locally. That's the first part. And then the second part says that on top of that, if I apply Alice's observable, I can think of it as a unitary, on the state psi, and I do this rotation, local rotation, it really has the same effect as applying the X observable on the EPR pair and nothing on the ancilla, on the extra state, and Z is with respect to A1. Okay, so maybe I can try to address your question now. Do you want to ask it again?
Up to you.
Yeah, sure.
Well, when they did the test, they exhausted the EPR pair that they can use to
I see.
report the state.
Yeah.
So,
Yeah, okay. So let's pause that for a second and let's answer that question, which is a little bit, okay, like finally, suppose that I accept all that stuff, but how do you use this for your protocol that, unfortunately, I might have erased now because I thought I wouldn't need it. Yeah. So how do you use that for your protocol? Because, like, fine, right? On the one hand, you can test EPR pairs, but when you're testing them, they're burning them. They're measuring them to demonstrate to you that they had them, but then, they're not actually using them. And then on the other side, you're going to ask them to use some EPR pairs for teleportation, but these are maybe other EPR pairs that you're not checking. And so how do you know that, So the way we're going to do it is that the actual protocol is going to be a probabilistic combination of the two protocols. The point is that with probability half, we're going to check the EPR pairs, and with probability half, we're going to ask them to do the teleportation. But in a way that server 1, which is the one that we're trying to check, doesn't know what's going on. So I'm not explaining that part, but you can disguise the protocol that I described earlier from the point of view. So in that protocol, server 1 was told qubit I, qubit J, and a basis to measure, okay? And so they could cheat when they're given that kind of question, which they know is, whereas when their question is, oh, could you please play CHSH game and here's your input, then they do the right thing and then. But what we do is that we disguise this protocol so that in the actual protocol, they don't know if I'm asking them to use the EPR pair as a test or to do the teleportation. And so they have to do the same thing in both, because from their point of view, what I'm asking them looks exactly the same, and they don't know if I'm testing or not. But I'm kind of skipping over the details of that. So originally I had thought I could give some ideas of the proof of that, but I'm not going to do it because there's not enough time. If anyone's interested, it's in the lecture notes, or we can talk about it at the break. I just want to emphasize maybe how strong this statement is. There's a lot, many things you can do using this. Why is it very strong? It's very strong because it's starting from what I think is a very weak assumption. This assumption is just that there's two servers and I can send them classical data, receive classical data back, and do a very simple statistical test. This is a very simple test, right? It's not even, I mean, statistical test is like a grand word. I'm just checking some parities and observing a certain number. But then only assuming two things. One is that quantum mechanics is the correct way to describe what the servers do, and the second thing is that these servers did not exchange information for the duration of my test. I get very strong consequences. The consequences is I know exactly what state they must have been using. Up to local rotations, it's an EPR pair. And I know exactly what measurement, at least one of them, but you can have a similar statement for the other one, has been making on that state. And so that's really the starting point, not only for achieving delegation protocols, which is what I tried to describe before. Before was just a reduction saying that in order to achieve delegation, the only thing you need to check is X and Z measurements, and this is exactly what this lets you do, checking X and Z measurements. You can do more things. You can check that they implement a circuit. You can check, there's some questions which are, well, this is about one EPR pair, but about two EPR pairs, three EPR pairs, four N EPR pairs, maybe a larger dimensional state. Can I have a little test like this that checks that they share a state of arbitrarily large dimension that has any kind of properties in terms of the entanglement that it witnesses? So there's a lot of research that goes in that direction. It also ties to, so I don't have time to talk about complexity theory, but this is also the basis for the study of interactive proofs, multi-prover interactive proofs in the quantum setting. And so there's complexity theoretic statements that you can make starting from that observation. Right? I'm not describing them. I just want to say that there's motivations outside of delegation. I think I'm promised to end on time, so I'll stop here. Maybe we have 1 minute for questions, and then Sandy will take over. Yeah.
Question. Do you have any thoughts on how you can be confident that the servers aren't, like, what you could do to enforce that they're not communicating?
Yeah. So the question is, well, how do you know that these two servers are not communicating with each other? So that's an assumption. That's a remaining assumption. I should have mentioned that the biggest open question of all is whether I can achieve delegation of quantum computation using a single server and no computational assumptions. Right? What I said right at the start of the lecture is that we know how to do it with a single server using computational assumptions, or information theoretically, but with two servers, and we don't know if we can do it. Okay. The question is, how do you enforce that they don't talk? Well, I mean, I don't have any better answer than the generic answer, which is to say, well, let's just put Alice in the middle, and let's require that the back and forth communication is fast enough so that in between the time where these servers have to beam back their answers to Alice, they don't have time to tell each other what their question was. And so that's just special relativity, so or general relativity. So. And this is done when people do experiments that verify this. This is exactly what they do. So they put a laser in the middle and they beam photons to Alice and Bob that are like a couple kilometers apart, and they do this fast enough that. Yeah. Sorry.
Any more questions?
So to prove the concordance of the protocols, you need the approximate version of this.
Yeah. So there's an approximate version. Yeah. I didn't state that, but yeah.
If not, let's thank